Hey guys, Mr. Betts here. I just want to walk through a few examples here where we're finding general solutions to differential equations using separation of variables. Again, this separation of variables process is something that we're going to use when we have x's and y's mixed together in a derivative. And the first step is to separate the variables. So notice that we're going to be multiplying by the dx. So the dx is going to be on the right side. So anything that has an x in it, we're going to keep on the right side. And then anything with a y in it will move to the left side. So we're going to multiply by dx on both sides. We're going to multiply by 2y on both sides. And so separating variables, we're going to have 2y dy is equal to 3x squared dx. Now, I do want to point out that the 2 right here and really the 3 here, those could go on either side. So the 3 and the 2 and really any constant, those don't have a variable themselves in there. So we could write this as 3 halves x squared on the right side. We could write it as 2/3 y on the left side. I'm going to leave it as this because thinking ahead, that's actually going to make things easier for the next step. So the next step, once we have variables separated, is we take the antiderivative on both sides. And the reason I wanted the 2 with the y is because the antiderivative of 2y is y squared. If I didn't have the 2 over there with it, we would have a 1/2 y squared, and we'd just have to deal with a fraction. Since this is an indefinite integral, we really have a plus c with this y squared, but we're going to take care of that plus c on the right side, and that'll take care of both. So we have y squared on the left, x cubed on the right, and then this plus c right here takes care of both constants, the one for the antiderivative on y and the one for the antiderivative on x. Now, the last step here for solving this and getting the general solution is to get y by itself. So to do that, we're going to take the square root on both sides. And we have to be careful here. Don't forget that when we take the square root on both sides, this y value here could be positive or negative, but when we square it, we get a positive. So to account for that, when we're solving an equation, we take a square root, we need that positive or negative there. So y is positive or negative square root of x cubed plus c. And as I mentioned in that introduction video, that plus c is embedded in the square root here. If you had the plus c outside of the square root, that would be wrong. It would actually represent a completely different family of functions. So make sure that we get the plus c in there when we take the antiderivative so that when we solve for y, that plus c, that constant of integration, is in the correct place. I also want to point out that this actually represents two kind of separate families of functions. So one of them is the positive side and one of them is the negative side. So we can make these functions look different by using the positive part or the negative part, and then by plugging in different values of c. So lots of different ways a solution to this might look, and we can actually use a slope field to kind of get an idea of what solution curves will look like in a coordinate plane. This example I have on here because this is a derivative that's defined entirely in terms of x, which is the independent variable here. So we can still solve a differential equation like this using separation of variables. We have solved these types of differential equations just using antiderivatives before, but if we separate variables, we get an expression that looks like this, which we can then take the antiderivative of both sides, and the antiderivative of 1 with respect to y is y. We take the derivative of secant of x to get secant times tangent, and then we have plus c. So when we did solve differential equations like this before, we get the same answer as if we do this with separation of variables. And it's really just a slightly different step here, an extra step in the middle where we get all the x's and all the y's on different sides, and then we take antiderivatives. It's not necessary to separate variables on an equation like this because there are no y's here, but it still works. On this one, we have our derivative defined as f prime of x, but notice that y is defined as f of x. So that means f prime of x is going to be the same thing as dy dx. So the first thing I'm going to do right here is rewrite this as dy dx is equal to negative x over y. Then to separate the variables, we're going to multiply by dx, and we're going to multiply by y. So we get y times dy equals negative x times dx. Then we take the antiderivative on both sides, and we get y squared is equal to negative x squared plus c. Sorry, that should be y squared over 2 equals negative x squared over 2 plus c. So one thing about an equation like this, when we're solving for y and we multiply by 2 on both sides, when we multiply our constant by 2, keep in mind that 2c is just a constant. It's generally not a good idea to just write a plus c here because this c and this c are going to be different. Specifically, this one is half as big as the other one, or I'm sorry, twice as big as the other one. So even though it's the same thing because it's just a constant, it's a good idea to put a plus 2c here because later on we're going to be solving for c, and we don't want to be able to plug the c value in one place but it not work in another place. So even though 2c is just a constant, I'm going to keep that as 2c so that this c value and this c value are the same. Then we want to get y by itself by taking the square root. So we're going to have y equals positive or negative square root of negative x squared plus 2c. And that is our general solution. Now, I do want to point out that in this form, it's not as easy to see. But if I rewrite this form a slightly different way by adding x squared to both sides, this is x squared plus y squared equals 2, not x, but 2c. And that you may recognize as the equation of a circle that's centered at 0, 0. So the solution to this differential equation is going to be actually a half circle because we're either going to get the top half of the circle or the bottom half of the circle. But this is the equation of a circle, and so the derivative that we are given here is going to have a solution that is either a top half or a bottom half of a circle. Okay, fairly straightforward here. Separate variables by multiplying by dx and multiplying by 3y squared. So we get 3y squared dy is equal to sine of x dx. Take the antiderivative on both sides. We get y cubed is equal to the opposite of cosine of x plus c. Then we're going to take the cube root of that. We get y equals the cube root of the opposite of cosine of x plus c. So again, that plus c is inside of the expression in some way. So make sure that we don't just put it at the end. Also notice that when we're doing a cube root or any odd root, we don't need the plus or minus out front because we can take the cube root of a negative number. We don't need to worry about that. So this is our general solution here. So last example, this one's a little bit tricky. It may be tempting to maybe subtract the square root of y on both sides to get that square root of y on the other side. However, remember our differential needs to be multiplied by the entire expression of y and the entire expression of x. So to handle that, to be able to do that, what I want to do here is actually factor out the square root of y. So this is going to be equal to the square root of y times the quantity 1 plus 2x. And so I'm going to separate variables using this expression here. So we're going to have 1 over the square root of y dy is equal to 1 plus 2x dx, and that dx is multiplied by the entire expression here. If it was not multiplied by the entire expression, then we wouldn't be able to do separation of variables. Now, for the left side, for the purpose of taking our antiderivative later, I'm going to rewrite that as y to the negative 1. That's going to allow me to use the power rule. So we're going to take the antiderivative So on the right side, we're going to have y to the 1/2. So I increase the power by 1. Then we're going to divide by 1/2, which is the same thing as multiplying by 2. On the other side, we're going to have x plus x squared plus c. Then we're going to divide by 2. So we get the square root of y is equal to x squared plus x plus c over 2. And then to get y by itself, we're going to square both sides. And we're going to get y equals x squared plus x plus c over 2 quantity squared. And that's your general solution.